The next speaker is Junhua Zhao. And let me introduce him also a little bit. And Professor Junhua is Associate Professor in the Chinese University of Hong Kong, Shenzhen, and also the Director of Energy Markets and Finance Lab, and also a scientist at Shenzhen Institute of AI and Robotics for Society. And before he joined current position, he was a senior lecturer and also acted as the principal research scientist of Center for Intelligent Electricity Networks in the University of Newcastle. He has 11 years of experience in the power industry in Australia. His research area includes smart grid, electricity market, energy economics, especially the data mining and AI. He published more than 200 research papers, including more than 100 papers indexed by SDA and 60 papers in the IEEE transactions. And especially he published papers have been cited more than 800 times with a H index of 45. And he is also the internal expert of Australian National Outlook and the co-chair of the IEEE Special Interest Group on Active Distribution Grids and Microgrids, as well as the secretary of the Asia Pacific Working Group of the IEEE focus on the smart building, load, and customer. So I think maybe that's the basic introduction about him. And actually, Professor Junhua will give us a speech. I think it's a really interesting topic and also a hot topic. He will introduce the work focused on the data-driven approaches to lower carbon energy economics. So welcome, Junhua.
Thank you, Professor Liu. So can you hear me?
Yeah, very clearly.
Okay. So can you please also grab me the co-host so that I can share my screen?
Yeah, wait a minute. I think maybe there's.
Maybe the Professor Khadija can grab me the co-host.
Yeah.
Let me see if I'm now more. Let me see.
Yeah.
Thank you.
You just pass on the host, okay?
That is now.
You can press the Junhua name.
Oh.
Yes, yeah. You are now the host. You're now the host.
Okay. Now I have the screen.
Can you imagine that? Can you imagine fatal error that I have disappeared now? And what would happen? Sorry.
No worries. Thank you very much. Thank you, Professor Liu, and thank you everybody for attending this panel. And I'm honored to be invited to participate in this panel. I'm Zhao Junhua from the Chinese University of Hong Kong in Shenzhen campus, and also with the Shenzhen Institute of AI and Robotics for Society. So today I will be talking about the data-driven approaches to low-carbon energy economics. So mostly I want to talk about the application of the data-driven techniques in two areas. One is the electricity market, another one is the carbon market. And my research mostly will find applications in the China's energy industry. Okay, so I will use that as a background. So firstly, the research background. Recently, the President Xi Jinping of China just stated in the United Nations General Assembly that the carbon emissions of China will reach the peak by 2030 and achieve the carbon neutrality by 2060. So, well, that largely means the carbon emission reduction has become a serious political and economic issue in China. We are expecting that a very large scale investment in the renewable energy and also other measures for controlling the carbon emission will happen very soon in China. And actually, starting from 2015, China is already undergoing the reforms of its energy system. So here the energy system covers both the electrical power systems and also the oil and natural gas industries. But mostly today, my talk will focus on the electrical power systems. So the most important component of the energy system reform is the electricity market reform in China. So China started the market reform in 2015. So the objective is to deregulate the power system. So very similar to what has been done in the Western countries. And we are introducing the electricity retailers into the market. And also the most important thing is we want to build the spot electricity market in China. So China has already have 8 spot market pilot provinces, including Guangdong, Sichuan, Fujian, and so on and so forth. And till now, already about 1/3 of the electricity customers has already entered the market. So actually the electricity market, its size is huge in China. So in this year, in 2020, so roughly 6.85 trillion kilowatt hour electricity has been sold. So you can imagine this is a very huge market. Another very important thing which is about to happen is the national carbon market. So China is about to launch the national carbon market in next year, so 2021. So the Ministry of Ecology and Environment has already issued the national regulations on the carbon emission trading management. So that marked the beginning of the carbon trading in China. And this will be a compulsory carbon trading market. And we estimate that the volume of the national carbon market in China will be huge. So the volume can be at about 4 billion tons of CO2. And the trading volume will reach about 100 billion RMB in China. So I think that marks the Chinese government has already determined, okay, has a very strong will to control the carbon emission, okay, using carbon market as a tool. So therefore, this is what is happening now in China, and we are trying to do research on modeling, simulation, and analysis of these two markets, the electricity market and the carbon market. So firstly, we need to have some theoretical framework, so how to analyze these two markets. Firstly, the electricity market, we all know that it's a very complex networked systems, right? So a lot of factors will affect the electricity market, the macroeconomy, the different industries, the policies, the seasons. So in the micro level, the fuel prices, right? The supply, demand, the power grid structure, okay? All these sort of factors will affect the spot electricity prices. So therefore, modeling the spot electricity market is a very difficult job. So theoretically, we propose to use this concept as the theoretical basis for analyzing the electricity market. So what is called the cyber-physical social system. Everybody is talking about the cyber-physical system for quite some time. And we think there may be another component which is important, which is the social components. So this is the cyber-physical system, right? We have the physical part, the energy production, transmission, consumption, and storage. And also we have the cyber system, right? The sensing, the communication, and the computing. And other than this thing, we also actually have the social system in the power system, because the system operators, the market participants, are the customers or the prosumers, okay? So they are all human, and actually they cannot be very accurately modeled in the cyber-physical framework. So we think we may use a different, or maybe we should say a extended theoretical framework to model this, okay? So we call this the cyber-physical social system. So in this system, we have the physical energy system, we have the customers, we have the market participants, and as well as the policymakers, the government. And the cyber system's job is to collect data from all parts of the system, from the physical energy system, also from the social parts. Okay. Then, based on the physical system data and the social system data collected by the cyber system, we actually have to build two models. One is for the physical system model, and another one is to build a social system model. Okay. And of course, they will have some interactions between each other. So here comes in the big data, because for some of the components of the cyber physical social system, in particular, I think the social part, we do not have a well-established modeling framework for modeling the social components in the power system. Okay. But now the big data in the power industry is providing us a very powerful tool for doing that. And we have many different sources of data in the modern power system, including the electricity market, the wide area measurement and PNU, the energy management system, SCADA, AMI, smart meters. Okay, so these are some of the data sources from the power systems. So actually, if we can better utilize this data, we can change the decision paradigm of power system from model-driven to data-driven. Okay, and in my research, my objective is to conduct what we call the panoramic modeling and decision-making of the electricity market. So why we call this panoramic? Because actually, when we do the modeling of the electricity market, we actually have three different levels. The model can be built at three different levels. The first one is at the micro level. We want to build models for customers' behaviors, or say the demand side consumption behaviors. Okay, so what are the behavior patterns of our customers? So in the middle level, we want to build models for generators and retailers. In other words, the market participants of the wholesale market. And ultimately, at the macro level, we want to have models for governments. So this is mainly used for market rule design. Okay, so we call this framework the panoramic modeling. Okay, so the next part, I would like to briefly talk about the key technologies we may use in my research. Firstly, at the micro level, we want to build models for the user behaviors. Okay, so we want to use the data fusion, combining deep learning and other machine learning technologies for modeling the user behaviors. The first techniques I want to talk about is called the super resolution perception. This idea is initially coming from the image processing area. So super resolution simply means when you have some low resolution image, we can use the machine learning or deep learning techniques to fill in the missing information to generate a high resolution image. Okay, so this is the original idea of the image super resolution. So we propose to use this idea in power system analysis as well. So in the power system, we have various sensors. Actually, we need a balance between the sensor sampling frequency, the meter cost, and the communication cost. Okay, so when you are sampling the data at a higher frequency, you have more data. Okay, you have better data to do the analysis, but you will have higher communication and data storage cost. Okay, so therefore, how about we using sensors to collect low frequency data, but we can use some kind of machine learning techniques to reconstruct the high frequency data from the low frequency data. Okay, so we call this the super resolution perception, or the SRP. We have already published a few papers on this topic. This is our initial work, so we welcome the suggestions from all the audiences here. The first work we published, we propose a new neural network structure. This is called Srpnet. So generally it consists of three components. The first one is the feature extraction, which consists of multiple convolutional layers. And the next one is we call the residual network. It consists of several residual blocks. So every residual block consists of one convolutional layer, one IELU activation function layer, and another convolutional layer. Okay, 3 layers together form a residual block. So the residual network consists of usually 7 to 8 residual blocks. And then ultimately we have a reconstruction block, which consists of convolutional layers. Okay. Using these techniques, we can see some initial results. So these are the ground truths, which are collected by the high frequency smart meters. The frequency, the initial frequency is at 10 Hertz, okay? And we want to do a super resolution with a super resolution ratio of 10. So that means we want to reconstruct 100 Hertz meter data from the 10 Hertz meter data, okay? So we fill in 9 points between every data point, 2 data points, okay? So this is the ground truth. So that means the 2 signals collected by the smart meters. This is the signals reconstructed by our algorithm, the Srpnet. And these are the 2 traditional interpolation methods, the linear and the cubic interpolation. So it's quite clear that our SRP have superior performances, and it can reconstruct large details, large parts of the details of the signals, while the interpolation methods will lose all the signal details. So we have already published 2 papers, one in engineering, so that is a journal managed by the Chinese Academy of Engineering, and another one, information sciences. The second techniques, I think, which are important for understanding the customer behaviors is the non-intrusive load monitoring, okay? So I think the audiences may be more familiar with this topic, so that generally it means we have a total load waveform measured by smart meters, and then we can use some machine learning algorithms to disaggregate the total waveform into the device level load waveform. So in that way, we can understand what kind of appliances are being used by this customer. So here we have already, we also have done some research works. The first one, we propose a non-intrusive load monitoring method based on the deep convolutional networks, okay? So this deep convolutional network consists of 18 layers, okay? The structure is shown here. And based on our experiments, so it has satisfactory accuracy, which is between 85% to 95%. We published this in the attribution section of Smart Grid. So we have also done another research work. So here we use an LSTM-based non-intrusive load monitoring method. And in particular, this one is applied on the non-intrusive load monitoring for industrial customers. So previously, most of the literatures, the research work is focusing on the residential customers, okay? So I think we are among the first to do this on industrial customers. So we have already collected around 100 industrial users data in China. And we have already submitted a paper to attribution sections of Smart Grid. And if our paper is accepted, we will also like to open source a data set, okay, for the industrial customers. So that is at the micro level, okay? In the middle level, we want to build models for the corporate behaviors, okay? To model the generators and the retailers' behavior in the electricity market. The challenges in the corporate behavior analysis is that inferring their bidding behaviors in the spot market is very difficult. We have some common methods. For example, we can make some assumptions. For example, we assume that they are bidding at their marginal cost. But this is obviously not true in the real world electricity market if we are looking at the bidding data. And some other existing methods, including game theory model, the bidding data mining, and the experimental economics. Okay. So we have done a few research works. The first one is we perform the data analytics on the historical bidding data. So how do we do this? We do the clustering of this power generation companies, okay? So we classify their typical bidding behaviors based on, firstly, what is the generation unit type? Is it a coal fire, or is it a hydro, or is it natural gas? And then by different seasons, okay? And also based on whether they are currently trading in the working days or holidays, or whether this is in the peak hours or the off-peak hours, okay? So based on this kind of classification, and then we do the clustering of the historical bidding data. And looking at these pictures, it's quite clear that we can find the typical bidding behaviors of power generators. So if we summarize the data analysis results, we can see that pretty much the all different types of generators, they all have their typical bidding behaviors. For example, the coal-fired generators, they usually bid at their marginal cost or their fuel cost, okay? If you're looking at wind power, they usually bid at a negative price, okay, because their marginal cost is actually negative. And for the hydropower, they usually bid at zero price or the ceiling price, the price cap. And also for the natural gas, the ceiling price is usually their typical strategy, okay? So based on the analysis of the historical trading data, I forgot to mention the historical data we used are coming from the national electricity market in Australia. Okay. So based on the analysis of the historical data, it's actually not very difficult to understand the typical behaviors of the market participants. Okay. And the second research work we have done is we're using something we call the inverse reinforcement learning to analyze the risk preference of generators, okay? So risk preference simply means whether this generator, the traders of this generator is risk-taking or risk-averse. Actually, by analyzing the historical trading data, it's interesting to find out that some time periods, the trader is risk-averse, and maybe in some other time periods, this trader will become risk-taking. So this is a new finding from the data analysis. For example, we also use the historical data from Australia. So we can see that this plant, they tend to avoid risk when the load exceeds 6,000 megawatts, but it tends to pursue risk when the load is between 5,500 to 6,000 megawatts. Okay, so as you can see, in different time periods, the behaviors of electricity traders will be different. So we have already published these on actually transactions on power systems. The last one, the macro level model. So we want to design models for the market rule design. So the major challenge in this research topic is if you want to use the historical data to assist the market rule design, it is impossible. Why? Because when you are designing the market, then it means that you don't have the market at the current stage, right? Then you don't have data, okay? You have no market, so you have no data. Then, but if you want to design the market, you do hope that your market rules are based on some solid model and analysis, right? We just don't want to propose some very naive and very unreasonable market rules. Then what can we do? So what we proposed is an approach we call the hybrid experimental learning. So the basic idea is that we want to have a economic experiment, okay? So, but this economic experiment consists of two kinds of participants. One is the computer agent, okay? So in other words, so this is an extension of the agent-based modeling. But on the other hand, we also hope that we can analyze and understand the behaviors of the two human players. Okay, so therefore, in our experiments, we not only have the computer agents, we also have the real human players. Okay, so in other words, it's more like playing a electronic games. Okay, we have computers. Okay, we also have human players. So this players, they will all participate in a market simulation. Okay, so in our research, this market simulation is the simulation of the spot electricity market in China. Okay. So this is the basic framework. This is the basic framework of our hybrid experimental learning. So as you can see, we have some computer agents, and the strategies, the trading strategies of the computer agents may come from either historical data or the analytical model. Okay, we can assume that they follow some, for example, game theory models or some other analytical models, and also coming from the generated model. So that means the model is generated from the experimental data. Okay, and then the real human agents and the computer agents, they will both participate in the market simulation. And every run of the simulation will generate some data. Okay, and we can use this data to train, we call the generative model. So that is a machine learning model. Okay. So we will repeat this process for several runs, and then we can have a analysis of the of what kind of market rules and what are the effects of this market rules on the market trading behavior. So here, these are some of the details of our hybrid experiments. Maybe we don't waste the time on reading all this. Okay. Okay, so the next part, I would like to introduce some of the applications of our techniques. The first one is, I think it's an interesting application that we have tried to apply the non-intrusive load monitoring and the super resolution perception to estimate the real-time carbon emission of industrial customers. Previously, the estimation of carbon emission of a company is usually very inaccurate. Okay, we usually tend to use the average carbon intensity times the energy consumption. Okay, and then we have the carbon emission. In this research, we hope we can use the smart meter data to estimate the real-time carbon emission. So the basic idea is when the smart meter generate the low frequency data, we use the SRP to reconstruct the high frequency data. Okay, and then we can use the non-intrusive load monitoring to get the device level energy consumption. And then from the device level energy consumption, we will calculate two things. One is the direct carbon emission. Okay, for example, if some of your appliances are burning coals or burning oils, okay, and that means you are generating carbon emission directly. And another emission, another type of emission is the indirect carbon emission. Okay, so for example, the air conditioner. So it consumes electricity, then it means that it is emitting carbon indirectly, right? So therefore, based on what kind of appliances this customer is using, and then we times the device energy consumption with the direct carbon emission factor and the indirect carbon emission factor. Okay, and then we sum them together. We have the total carbon emission of a industrial customers. So we published a conference paper on this topic. It just been published on the International Conference on Smart Grids and Energy Systems in this year. So this is the network structure we use to do the non-intrusive load monitoring in this paper. It's a combination of the convolutional neural network and the LSTM, the long short-term memory network. This is the result of the non-intrusive load monitoring. So this picture is interesting. It shows the real-time carbon emission of a steel mill in China. Okay, so this is the real data. The blue line represents the total carbon emission. So as you can see, it's time varying. Okay, so when this steel mill is shut down at around 4 o'clock. Okay, so the carbon emission drops very significantly. And the red line, the green line is the direct carbon emission. So it jumps to 0, okay, after 4 o'clock, after 16 o'clock. And the red line is the indirect carbon emission, okay. So as you can see, so at the after the office hours, we still have some indirect carbon emission. That is largely because you are still consuming electricity, the lights and the air conditioner. Okay. So these are other results. Another thing we have done on the carbon emission is the data center carbon emission optimization. So nowadays, while we are using a lot of AI and big data technologies, also in power system analysis, but actually the AI and the big data, because they are computing, so they are consuming a very large amount of energy as well. Okay, so the data center's energy consumption will account for nearly 10% of the energy consumption in the whole world. So therefore, we want to manage the carbon emission of data centers. Actually, we have formulated a optimization model. So in this optimization model, the objective is not only the energy cost, we also consider the environmental cost. So that, in other words, we try to minimize both the energy consumption cost and the carbon cost, okay, in the real-time scheduling framework for the data centers. Okay. So to optimize the real-time carbon emission of data centers, we need to calculate the marginal nodal carbon intensity. So this marginal nodal carbon intensity is calculated from power flow analysis. Okay, so we do the power flow analysis for the first time, and then we increase the demand one of the nodes by 1 megawatt, and then we recalculate the optimal power flow, and then we calculate the difference of carbon emissions in these two scenarios, and then we have the marginal carbon intensity. And using this marginal carbon intensities, then we can calculate what is the carbon emission of a data center on this node. Okay. And here the assumption is we have multiple data centers, and then the computing task can be shifted between these multiple nodes. Okay, so when some nodes have lower carbon intensity, the computing task will be shifted to this node. So that is the general idea. We have done some experiments. So it's based on the IEEE 14 bus testing systems. We have tested for very commonly used machine learning models, the data augmentation, the image inplating, highlight detection, and the post-to-sec. So as you can see, using our models, so the total training cost, so here the training cost equals to the energy cost plus the carbon cost. So the total training cost will be reduced by 14%, 9%, 11%, 10%. Okay, so it's quite obviously our model can save the energy and the carbon cost of a data center. Also, what we have done on the electricity market simulations, we have applied this on the offshore wind power. We analyzed the impacts of the offshore wind power on the China's electricity market. I don't want to waste the time talking about the details. So actually, we have done simulations on several different scenarios. For example, in the winter, when we have a pretty strong wind power. As you can see, when we add the wind power into the market, so the wind power will cause the spot electricity market at this node drop to the price floor. Okay, so the wind power has a very significant impact on the spot electricity market results. So here you can see similar results as well. So this is for the summer's scenarios. Okay, we have also applied the hybrid experiment approach on the son of the monkey rule design problems. So here we use this on the gas turbine generators subsidy design. So in the Guangdong's spot electricity market, so the government is considering giving subsidies to the gas generators because their marginal cost is too high. But we do need peaking generators in the market. Okay, so we want to give them some subsidy. But what kind of subsidy we should provide is the problem. Okay, so in our research we have done the hybrid experiments. Okay, to analyze what kind of subsidies can be provided and what are their effects. So let's ignore the details. We are using the hybrid experiments to do that. So here is the results. As you can see here, without the subsidy, these gas generators, so they tend to place all of their capacities at the highest price band. So in other words, they have the incentive to drive the spot electricity price up. Okay, because they want to earn more money. But with the subsidy, as you can see, he tend to move some of its capacities to the lower price bands. Okay, so in other words, so we have used the subsidy to reduce their incentives to bid at higher prices in the market. We can also have many other applications of our approaches on the energy economics problems. So here are some of my outlooks. What kind of problems what kind of things we can do. One thing is when we have the smart meters, we have collect a lot of customers' data. We can actually use that to analyze the prosperity of different industrial sectors. Okay, the textile, the metal, the chemical, construction, medical. Okay, so using their electricity consumption data, so we can firstly analyze. So are they in a very good situation, or they are in the downturn, and the government can decide whether they need to provide some support to different industrial sectors. Okay, to understand what is the current situation of these industrial sectors. Another one, of course, is the electricity market analysis and also the electricity finance in China, because China is not only building the spot electricity market, so it also has the plan to build a financial electricity market. So that means electricity futures, electricity options, and so on and so forth. So we can see applications of our techniques in this kind of areas. And the next one, of course, is the carbon asset management and the carbon finance. So because the carbon market is about to launch in next year, so very soon. It's a huge market, okay? Market size nearly 100 billion yuan. So we are expecting that we can apply the analysis techniques we have introduced in this talk in analyzing the carbon market in China. Okay. Okay, so that pretty much summarizes my my talk. Thank you very much.
Thank you, Professor Junhua Zhao. Actually, I can see that many people are really interested in your topic. And here, 4 questions for you. Maybe you can give some feedback to the questions, okay?
Yeah. So the first question from Professor Yan. I mentioned carbon market potential for gigaton CO2 in China. Can I give more information on the current status of the trading volume carbon price and when it will reach to the gigaton trading? Currently, the trading volume in China is not very large. It's about 1 billion RMB per year, roughly like that in China, because it's still in the trial trading stage. But according to the plan of the Ministry of Ecology and Environment, the compulsory national carbon market will start to launch in early next year. So that means the first half of next year. So once that market starts, we estimate. Actually, I have discussed this with some other people in the state grid, and also some other people in the finance industry. So the estimate are not very different. Okay, so we pretty much all estimated that when the carbon market starts from next year, from 2021, it will reach the 100 billion RMB size. So I hope that has answered your question. Also, another question is, in addition, electricity sector, any other sectors will be in the carbon market in the future? Yes. So according to the Ministry of Environment, in total, 8 sectors will be introduced into the carbon market. But in the early stage of the carbon market, so that means in the first maybe 2 or 3 years, only the power generation sector will be introduced in the carbon market. But in future, for example, the transport, the oil and natural gas, the industry, agricultural, so all these sectors will be introduced into the carbon market in the future. But when, we don't know at the current stage. But what we do know is in next year, the power generation sector will be under the regulation of the carbon market. Okay, so another 2 questions from Professor Tazia. So question 1, based on which criterion you select the sampling frequency of your data acquisition system? Well, actually, when we have this, when we are doing this SRP research, the sampling frequency is determined by the state grid because we are doing an industrial research project for state grid, and they provide us the data. So the data they provide is at 100 Hertz. To be honest, I'm not very sure how do they determine that sampling frequency. And of course, that sampling frequency is actually higher than most of the smart meters in China. That is a research project. Okay, so they are placing some high frequency smart meters to do some testing. So that's question 1. Question 2, can you explain to us what is the difference between ordinary AI networks and those based on deep learning? Okay, I think my personal understanding is that the difference between the traditional neural network is that it usually has only 2 to 3, and usually no more than that. Usually 2 to 3 hidden layers. But for the deep learning, usually most of the deep learning networks we use today have at least 10 to 20 hidden layers. And some of the large scale networks, they have hundreds or even thousands of hidden layers. Well, that's from the network structure point of view. Theoretically, when you have more hidden layers, you are doing more complicated feature mapping on each hidden layer. So that in other words, when you have more hidden layers, you are doing more mathematical mapping in every hidden layer. That will introduce more complicated and usually more effective features, okay, for your neural networks. And the past experiences in deep learning is that these features produced by the more hidden layers will improve the accuracy of the neural networks. So I think that is the basic differences. Another question from Professor Yan is, can I?
Yeah, I saw that. I think there are so many questions for you. Maybe you can leave your answer also in the chat box, okay?
Okay, so maybe, yeah, I can type my answers in the chat box, okay? So save the time for other speakers. Sorry.
Yeah, thanks
okay,
a lot.
Thank you very much.
Yeah, and by the way, Professor Yan also shared a very useful link for us. The link is about the interesting information on data center energy consumption at the global scale. I believe many people are really interested in this. So if you have some requirements, you can use it, okay? So let's move on to the